Takandam, Inosovers. Music. For as long as humans have watched the sky, they've wondered whether Earth was unique, whether other Earths might be out there somewhere. For centuries, we knew of only one solar system, the one our planet Earth inhabited, circling the star we call the Sun. Now planet hunters are finding new planets far across our galaxy, and some of them may be just like ours. We are very, very close to discovering the first Earth-like planets ever found elsewhere in the universe. Wow, I am absolutely stunned at this. Using exciting new technology, the Kepler Space Telescope has revealed a previously invisible world of undiscovered planets, and if many are Earth-like, can there be any doubt about life beyond our solar system? The chance that life is out there somewhere in my mind is 100%. Music on the island of Maui at an observatory above the clouds on Mount Halaka, a rare event called a planetary transit, has drawn a crowd. Standing on the rim of an ancient volcano 3,000 menars above the beaches, amateur and professional astronomers are about to watch the planet Venus cross between the Earth and the Sun. Yeah, right there. I think they see contact. Yeah, we got it. Wow. Transits of Venus have been observed since the 17th century. This is cool. But now, modern planet hunters can see something the early astronomers never could. As soon as Venus begins its trek, the brightness of the Sun dims ever so slightly. With new super-sensitive light detectors and a space-based telescope, astronomers are now looking for the dimming of light caused by otherwise undetectable planets crossing in front of distant stars. Transits have come to the forefront of astronomy again, and in fact, transits are turning out to be one of the best ways to discover a twin of the Earth orbiting a distant sun. Carefully measuring this dimming of light is the technique being used by NASA's Kepler Space Telescope in the search for exoplanets, planets beyond our solar system, passing in front of their stars, just the way Venus transits the Sun. If the Kepler telescope were looking back at our solar system from a nearby star, it would be able to detect the dimming of the Sun temporarily while a planet the size of Venus is crossing in front of it. A Venus or Earth-sized planet would dim the light of its star by only 1/100%, a change too small for even the largest telescopes on Earth to see through our turbulent atmosphere, which is why Kepler is observing these stars from space, because we can make a much more precise measurement of the brightness of stars. But the vastness of space makes this an enormous task, so instead of a random search, NASA has focused the Kepler telescope on a specific patch of our Milky Way galaxy, with 150,000 visible stars. By staring at the same large group of stars for a long time, they are much more likely to achieve their mission, finding Earth's twin. Music? At the south end of San Francisco Bay, astronomers at the NASA Research Lab have studied hundreds of thousands of light curves. They're the dips of light caused by planet transits. These signals from the Kepler Space Telescope are physical evidence of planets beyond our solar system. Among them may be another Earth. So I'm curious if this is real or instrumental. Astronomer Jason Rowe from Mississauga, Ontario gets to look at the raw data before anyone else. His job is to sort the real discoveries from the false alarms. A brief look into this suggests that we have about 50 very preliminary candidates that may be very small. Planet hunters from NASA and from research labs around the world have gathered for a look at the latest download of data from the Kepler telescope. As far as we're concerned, there's a transit-looking event here and we should look at it closely. And Kepler so far has found an avalanche of planets, mostly small planets, nearly the size of the Earth. We found almost 3,000. And what's remarkable, and this we had no idea about beforehand, is that we're finding more and more of the smaller and smaller planets. There are a smattering of Jupiters, there are a few more Saturns, there's a handful or more of the Neptunes so to speak, but there's an actual flood of planets that are the size of or a little larger than the Earth. Earth's size matters because Earth is the one planet we know as life. If we find another that seems like Earth in most ways, a solid rocky planet with liquid water, then it too may sustain life. Any smaller and it may not have enough gravity to hold on to an atmosphere. Much larger, and it might be made of gas or could have other unknown but deadly conditions. We finally started finding candidates that were Earth-size, maybe one or two at first, and then with the next download of data, we found hundreds of them. And now, we're at the next tipping point where we're finding a few candidates that look Earth-sized and looked habitable. So I'm now expecting with our next group of data that we're just going to be finding them hands over fist. We are alive at a very special moment in human history. in the next few years, there's going to come that first moment when humanity learned, are there other planets like our own out there in the galaxy? And might we in fact find life upon them? And if some of those Earth-sized planets are capable of supporting life, one member of the Kepler team, Jill Tarter, can now refocus her search for intelligent life. Kepler is showing us worlds, unlike any that we've seen in our own solar system. Is that more habitable or less habitable? We just don't know. But we do know that life, at least life as we know it, is a planetary phenomenon. Now we know there are lots of planets and we know where to find them. So that's where we're looking. The Kepler Space-Orn telescope will be something like Armstrong stepping on the moon. It'll be something like the discovery of penicillin. You know, those moments that transform the sense of who we humans are as a species in our voyage to answer the big questions in the universe. Answers to the big questions may be just around the corner. But Kepler is already providing a wealth of new data about other solar systems. Ray Jaward of the University of Toronto says the Kepler mission has opened the door to all kinds of strange new worlds and helped us understand how planets form in the first place. In terms of how planets form, all of the evidence that we have point to planets forming out of disks of dust and gas that circle young stars when they're born. And it's out of these disks that we think planetary systems come to be. So these, we believe, are the birth site, the planetary nurseries. But some of the new multi-planet systems discovered by Kepler are very different from our own solar system. We have found very big planets very close to their stars. We found planets in orbits that are not at all circular. They're very eccentric, very elliptical orbits. And most recently, Kepler found a system of planets where you alternate. You have a gassy giant planet, then a small rocky planet, then a gassy giant planet, then a small rocky planet, and then another gas giant as you travel outwards from the star. And I haven't heard any good explanation about how you might make such a system. But the most important new world discovered by Kepler will be those Earth-sized planets in the so-called Goldilocks zone. The search for life elsewhere is essentially a search for water. So when we're thinking about other worlds that might be habitable, we're thinking of planets that are not too far from their star and not too close to their star, such that the temperature would be just right for liquid water on the surface of such planets. So these are the planets that we've come to call Goldilocks planets. Just like Goldilocks, who was sampling the porridge, and you know, she found a bowl that was like too hot, and then one that was too cold, and then the one that was just right where the temperature at the surface would be between the freezing point and the boiling point of water. And that's what we refer to as the habitable zone, the Goldilocks zone. In our own solar system, Mercury and Venus are too close to the sun and too hot for life as we know it. Beyond Mars, it's too cold. The orbital path of Earth, the only place we know for sure that life exists, is in the center of our star's Goldilocks zone. Not too hot, not too cold, just right for life. So, this is going to change for every different star that we look at. So if the star is much hotter, then we need to find planets that are in further orbital zones or further orbital periods. Likewise, as the star is cooler, we'll be looking for planets that are much closer in. Finding distant stars that are similar to our sun is one thing, but how do you find planets? Tiny specks by comparison, so small you can't even see them. Of all the planets Kepler has discovered so far, not a single one has been seen through a telescope, much less by the human eye. The problem, according to astronomer Jamie Matthews, is glare. When you ask people how should we look for planets, the intuitive thing is take a picture. You know, we've got gigantic telescopes, we've got these sensitive CCD cameras, we see these beautiful images, you know, even taken from low Earth orbit by the Hubble Space Telescope of the planet Mars. And the problem is that planets are just intrinsically faint. A planet like the Earth, as seen by alien astronomers, if they're out there, would be about 1 billion times fainter than the Sun. To illustrate how hard it is to see a planet hundreds of light years from Earth, Jamie Matthews asks us to imagine trying to see a flashlight beam next to a lighthouse, and you're staring right into the lighthouse beacon. You can't see the flashlight, so we can't see an Earth hiding in the glare of the equivalent of the lighthouse beacon. For the early planet hunters, glare was an insurmountable obstacle until the late 1970s. At the Dominion Astrophysical Observatory on Vancouver Island, 2 Canadian astronomers began working on a radical new approach. The real fathers of planet discovery are Bruce Campbell and Gordon Walker. They had the audacious, and totally original idea that you could detect planets around other stars, despite the planets being invisible by watching the star wobble around, as the planet pulls gravitationally on the star. You can't see the planet because it's lost in the glare of the star. Bruce and Gordon understood that, but they knew that you might be able to see the star wobble in a storage locker outside the telescope dome. Let's give it a go. A steel contraption. Hey. Wow, look at that. That changed the history of planet hunting lies wrapped in plastic covered in cobwebs and grunge. There's the old cell. Remember this? Oh yes. These are protection suit. Everything's there. Only 30 years ago. No planets had yet been discovered outside our solar system. Gordon Walker and Stevenson Yang were part of a team of researchers from the University of British Columbia who thought they could find distant planets by measuring the wobble as a planet's gravity tugged on its parent star. I'll look at you, you look at me. Oh, hi go, I didn't see you. To do that, they needed to be able to see the color change caused by the star's wobble. In the same way that the sound of an engine changes as it passes, in what's known as the Doppler effect, light coming from a star changes color ever so slightly as the star moves toward or away from the person watching it. In other words, they were able to use a telescope like a radar gun to clock the speed of a moving star. At the time, no instrument could take a light measurement precise enough to do this. How they solved this problem would revolutionize planet hunting. The light comes down from the telescope up here, strikes that mirror, is sent sideways into this room here, which contains a spectrograph, and we put the hydrogen fluoride tube into the telescope beam right here, so that the light went through it and into the spectrograph. Walker Yang and Bruce Campbell had the revolutionary idea that passing the star's light through a gas would build a sort of ruler into every light measurement, making it possible to see much smaller color changes from the star's wobble. They decided to test the theory by measuring Jupiter's tug on our sun. By replacing old photographic plates with one of the first ever digital cameras, they vastly improved the accuracy of their measurements, so this gave us a hugely better signal. Then I realized that suddenly we had, in our hand, the ability to measure velocities with enough precision that we could detect planets around other stars. Even though the stars are hundreds of light years away, they figured out a method to determine if a star was running at you or away from you at plus or minus human running speed. As the planet yanks on the star, you get a number of times in your scientific career when things become fairly obvious that you're on the right path. And that was one of them. Gordon Walker and Bruce Campbell are the pioneers of exoplanetary science. They were the first people that really had the sensitivity to find planets. The Wobble method worked. They did find a planet, the first ever found outside our solar system, but they had reasons to doubt it and never made the claim. The parent star is a giant star. So how could a planet be so close to a giant star? There were all kinds of reasons why that might be a wrong interpretation, so the paper they wrote in 1987 said they might have detected a planet but they couldn't be certain. Our paper actually had a question mark. Is it a planet? My gut feeling was that in fact, we did have a planet. Campbell and Walker did, in fact, detect the first planet outside of our solar system, and it's just that they applied the proper scientific caution to their announcement. All the early planet discoveries were made by ground-based telescopes with heavy light-collecting mirrors and plenty of room to install the bulky equipment that measured a star's wobble. But the next stage of planet hunting would be very different. It was time to put telescopes into space. By 1990, Hubble had proved you could get spectacular results with a relatively small mirror just by getting above the blurring effects of the Earth's atmosphere. A decade later, a group of Canadians came up with something even smaller, but no less effective. A space telescope that would help take planet hunters to the next major breakthrough. When Canada's first space telescope, called MOST, was still on the drawing board, lead scientist Jaime Matthews had no intention of looking for distant planets. MOST was designed to do seismology of stars. Once we had designed it and started to build it, I realized we can search for other planets there with a sensitivity that nobody else can get. A metal box not much bigger than a suitcase, the MOST satellite was installed on top of a Russian rocket and launched into space on June 30, 2003. MOST is Canada's first space telescope. We nicknamed it the Humble Space Telescope. At a fraction of the cost of Hubble, with a primary mirror the size of a dinner plate and a super-sensitive light detector, MOST could detect a planet transit. Proof that the design of the Kepler telescope, then still in the planning stage, would work. MOST went into space almost 7 years before Kepler was launched, and so it was proof of concept. Here you had an instrument in orbit that was looking at stars, and getting this kind of phototrick light measuring precision, and so that had to have helped in terms of the resistance, to funding Kepler. The prototype for the Kepler telescope was basically a big light detector married to a digital camera, a lot like most, only larger and more elaborate. Bill Barouy, the visionary engineer who designed it, did have a hard time selling the idea. It took 2 decades and 5 different proposals to convince NASA that the Kepler telescope would work. The success of Canada's MOST project and confirmation that distant planets were indeed out there, causing stars to wobble, helped turn the tide. In March 2009, a Delta I rocket lifted Kepler off the pad at Cape Canaveral. The mission objective was to find Earth-like planets by conducting a survey of 150,000 stars in our Milky Way galaxy. A grid of super-sensitive light detectors captures images that are streamed back to Earth, masses of new data every year. The Kepler mission requires these large numbers of stars, 150,000, because it's so rare that a planet will have its orbit so nearly edge on that the planet happens to cross in front of the star, blocking the starlight. Most of the planets, of course, reside in randomly tilted orbits, 30 degrees, 60 degrees maybe, face on. But in fact, the only ones we can see with Kepler are the planets that actually just cross right in front of the star. Kepler isn't simply about finding one Earth twin out there, elsewhere in the galaxy. It's actually, an even more important thing to find out, is how common Earth-like worlds are. It's doing kind of the long-form census of the planetary population of our part of the galaxy. It's basically answering the question, if there are Earths out there, how many of them are there? How common are Earth-sized planets? How many of them are in the Goldilocks zone, that could at least satisfy one of the conditions for supporting life? Among the nearly 3,000 possible planets discovered thus far, they've found big ones, small ones, hot and cold ones, even a planet named Kepler 16b that circles a double star. So, it would have a double sunset every day, just like a scene from Star Wars. The nice thing about this one is you can see a beautiful-looking transit up there. It's quite clear that it's a transit. With each new download of data, they get a little closer to finding a planet the same size as Earth in the Goldilocks zone. Final confirmation of the Kepler discoveries will be made by a ground-based observatory like the Twin K telescopes in Hawaii. After watching a star blink from a transit, you need to see it wobble just to be sure. KK's primary mirrors are each made of 36 hexagonal segments operating as a single unit, more than 14 tons of ceramic coated with aluminum at the top of the dormant Monica volcano, above most of the moisture and turbulent air that can blur a telescope's image. The Keck Observatory has the best possible view of the same stars that Kepler has been tracking. But instead of watching 150,000 of them at once, Keck will zoom in one star at a time to rule out false positives. Laser beams create an artificial star 20 kilometers up to help telescope optics adjust for the remaining atmospheric interference, taking most of the twinkle out of the real stars and creating images as sharp as if taken from space. The control room is below the clouds and halfway down the mountain where astronomers like Jeff Marcy and David Soderblom will work through the night on a long list of Kepler targets. We have various goals with these observations. The primary one is to verify that the planets actually exist, that we weren't being fooled by the data. They are linked by a live video feed to the telescope operator at the top of the mountain and to a research colleague in Berkeley. How's the scene, Joel? I can see fine. And this is the one that's really of interest. This is KOI Kepler Object of Interest. That's awesome. The light spectrum of each star is examined for the color shift that indicates the wobble from the pole of a nearby planet. A wobble can confirm that a planet is there, but it can also reveal a planet's physical characteristics. We zoom in on spectral lines and we see this. The most exciting thing we're doing is to try to measure the wobble of the stars as they're yanked around by their planets, gravitationally pulling on the star, giving us a measure of the mass of the planets. They know this one is Earth's size and rocky, but there's a catch. Unfortunately, this planet orbiting this star is very close to the star. So close that it's blowtorched to a temperature of about 1,500 degrees C. You could cook a chicken in a millisecond on this planet, so this Kepler planet candidate is too close to its parent star and therefore way too hot for life as we know it. But it's still an important discovery. We are still working hard to find truly habitable planets, and this is a planet that's exciting because it's the size of the Earth. It has a density, meaning it's rocky like the Earth, but it's not in the Goldilocks zone. The good news is there are lots more out there. All of the planets Kepler's found that are between an Earth size and 4 times the size of the Earth, just this huge swath. We knew nothing about that before Kepler. And then look at all these planets that are smaller than the Earth. Incredible. The Kepler team is confident that Earth's twin is there in the data, and the holy grail of astronomy may be found within months. On a shoulder of rock near the top of Mount Hopkins, in Arizona, a fully automated array of 8 robotic telescopes is ready for another night of planet hunting. This is the Mirth Project. David Charbonneau from Ottawa, a professor of astronomy at Harvard and member of the Kepler science team, is hunting for planets that are closer to home. The great thing about Kepler is that it's going to tell us how common Earth-like planets are. The bad part about Kepler is the stars that Kepler is studying are too far away, and so what we need to do is take the knowledge of Kepler and then design a survey that looks at only stars that are extremely close to the Earth. The closer the stars, the easier they are to see, which is why small telescopes will do the job, but it takes 8 of them to search enough stars one at a time. So Charbonneau and his colleagues created software to automate the process. If a telescope spots a star that starts to dim, it automatically knows to swing back and check again. They'll stop what they're doing, and they'll slew over, and then confirm whether or not there is in fact a planet there. Having learned from Kepler that so many stars do have planets, Charbonneau's team is looking for ones close enough to have detectable atmospheres and signs of life. Music. If you really want to understand what a planet is made of, how it was formed, and ultimately whether it has life on it, we need to develop methods to study the atmospheres of planets. So as a postdoc, I was the first person to measure to actually detect an atmosphere. Then I began to think, well, maybe one day we'll have a machine that can find small rocky planets that might have life in them, and then we'll use the same method to go and study the atmospheres of those planets and look for chemical signatures of life like oxygen. Here we are 10 years later, and that's playing out. That's what Sarah Seeger from Toronto is doing as well. Another Kepler team member, she's come to the desert north of Roswell, New Mexico, to test the lens assembly and software for a new generation of space telescope. Her project will, like Mirth, focus on planets closer to Earth. Once Seeger and her colleagues work the bugs out, this system will be launched into space in a satellite no bigger than a shoebox. We're testing a nano-satellite called Exoplanet Sat. Exoplanet Sat is like a second-generation MOST. It's designed purposely to look for planets that go in front of their star as seen from Earth. What they hope to do is capture a bit of starlight as it passes through a planet's atmosphere, like watching sunset on a world far away. As the planet goes in front of the star, some of the starlight can shine through the atmosphere and we can pick up what we call spectral features, or we can pick up fingerprints of molecules in the atmospheres of those planets. So you could think of it like a sunset, like our sky is blue but it's red during sunset. And that can tell us about the particles, the sizes of particles in our atmosphere are scattering in the sunlight. And the blue fingerprint of oxygen is what they're really looking for. Music. When Apollo 8 astronaut William Anders snapped this famous 1968 picture of Earth rising above the moon's horizon, our atmosphere gave off a distinctly blue tint. More recent photographs make the same point in high definition. Sunlight bouncing off the Earth looks blue mainly because of surface water and gases like oxygen in our atmosphere. And the oxygen is there primarily because of all the life on Earth. The Earth's atmosphere has been constantly changing due to the different organisms that lived on the Earth at that time. And of course, the most obvious current chemical signature of life is just this massive abundance of oxygen. The only reason why the concentration of oxygen is so high on Earth is because of life. No other planet in the solar system has significant oxygen in the atmosphere, and so it's this very clear signature that there must be life on the planet. It's one thing to see a crystal clear picture of the Earth, but what if your camera were billions of miles away in space? How much could you tell about a distant planet just by its color? In 1981, as the Voyager 1 space probe zoomed past our solar system, nearing the end of its primary mission, astronomer Carl Schon persuaded NASA to turn the camera around and take one last picture of our home planet. From a distance of 3 and 12 billion miles, the actual image of the Earth looked like a pale blue dot in the interplanetary dust. What if a photo like this were all we knew about another planet? Music scientists at the University of Washington in Seattle are studying a computer model of the Earth to learn how our pale blue dot can someday help us decode similar dots far beyond our solar system. When we find these extrasolar planets orbiting around other stars, we won't be able to see things like continents or oceans or anything like that. that planet is going to be a tiny little dot, and from that tiny little dot we have to figure out as much as we can about this world. We can always run it with, and without the N2 and 2Ca, and with, and without CO2 to also get a sense of how lots and lots of CO2 is going to affect this region of the spectrum. We do have a three-dimensional model of the Earth. We use that model of the Earth to try and understand, for example, how detectable are oceans at a distance of 10 parasecs away in the presence of realistic clouds. How detectable are the continents? Can we pull any of this information out when we see only a pale blue dot? The old model isn't working over the Pacific. Even the Earth is proving hard to analyze. Their model looks dark where they expect it to be bright. The model that we've been working with actually makes the assumption that ice clouds are thin. So, we probably need to go in and actually make the model more realistic by allowing ice clouds to be thick and reflective. After fine-tuning their computer model, researchers at the Virtual Planetary Lab then used the software to predict what other planets with different kinds of atmospheres and different colors of starlight might actually look like. By looking at what light hit the ground and by looking at what life on Earth had done with that light, we were able to come up with rules that predicted where the pigments would be for the plants, and from that, we were then able to determine what color those plants would be. The different spectrum of the star actually changes the composition of the atmosphere. Orbiting around an F-star, you in fact get a lot of blue radiation coming down to the surface, and so the plant was able to use that, which meant that its color was probably more likely to be in this sort of yellow-orange range rather than the typical green that we see on the Earth. Or music. What we're doing now is we're evaluating all the gases produced by life on Earth. And we're asking ourselves, in a different environment on another planet that might be bigger or smaller or have a different atmospheric composition, which of these gases might appear and might be able to accumulate in the atmosphere and be observed by us as biosignature gases. So we hope to see gases on other planets that might not be oxygen. It could be something else that shouldn't be there, and that we then can assign some kind of probability that life is on the surface generating that gas. The big challenge, of course, is we wouldn't know whether you're looking at green slime for a civilization, but the odds of finding some form of life seem to be increasing because there are so many stars with potential Goldilocks planets. Our sun is so bright and so hot that life as we know it would be impossible on nearby planets like Mercury and Venus. But many of the Kepler stars are cooler and smaller than our sun, which means a planet like Venus in the same orbit around a cooler star might be able to sustain life. In other words, there may be more Goldilocks planets than we thought. We have two good candidates right now that look like they're Earth-sized and they're in around cooler stars. So as we characterize and understand the stars better, we're also able to characterize what is the Goldilocks zone around those stars. But there may be a problem redefining the Goldilocks zone, because even if the star is cooler, a closer orbit may cause such strong gravity that the core of the planet overheats, creating a volcanic surface inhospitable to life. That gravitational squishing results in energy being deposited into the planet, which can heat the planet up. And in some extreme cases, it's possible you can boil off an ocean that way. At this point, nobody really knows where the Goldilocks zone would be around a cooler star, but these modern-day Galileo remain optimistic that they will find Earth's twin and that there will be life out there. The next obvious question is, could it be intelligent life? The search for Earth's twin began with a simple idea. Look for distant planets by watching the light dim, just the way it does in a total eclipse of the sun. The ultimate example of a transit. There it is. Now, because of the Kepler mission, possible Earth-like planets are being identified, and supporters of SETI, the search for extraterrestrial intelligence, couldn't be more thrilled. At the Allen Telescope Array in Northern California, SETI has accelerated its search. For all these years, SETI researchers have been pointing their telescopes, optical and radio, at stars. Stars that we thought probably would have planets around them potentially in the habitable zone, but we didn't know. And now, thanks to Kepler, we know thousands of planetary systems. So, we're now looking where there are planets. Some of those planets are actually at the right distance from their star to have the kind of attractive climates that we associate with life, liquid water on the surface and atmosphere and all that. So, clearly, we're going to point our antennas in those directions. Terabytes of new data are captured every day, and now because of the Kepler discoveries, SETI is reaching out to thousands of citizen scientists, inviting them to log on and join the search. And we're going to ask you, do you see any patterns in there? We've tried to find a signal that nature cannot produce. So in the case of radio searches, we're looking for signals that are compressed in frequency. They show up at only one channel on the radio dial. Their energy isn't spread across many channels. Nature can't do that. And so we're looking for these obviously engineered signals. At one point in her life, Jill Tarter wanted to be the first woman on the moon. She became an astronomer, the inspiration for Jodie Foster's character in the movie Contact. She's now a member of NASA's Kepler science team, but her passion remains the search for intelligent life.